the deeper humanity learns to look into space, the stranger the universe becomes. For centuries, the night sky appeared calm and distant, a quiet scattering of faint lights whose secrets seemed far beyond reach. Even after the invention of the first telescopes, the cosmos still revealed itself slowly, layer by layer, as though it were reluctant to surrender its history too easily. Each improvement in technology brought a new glimpse further back in time, and with each glimpse came a new understanding of how the universe had unfolded. The reason astronomers can peer into the past at all is surprisingly simple. Light takes time to travel. When a telescope captures the glow of a distant galaxy, that light has often spent billions of years crossing the vast emptiness of space before finally reaching Earth. Observing distant galaxies, therefore, means seeing them not as they exist today, but as they once were when the universe itself was younger. For decades, scientists built a remarkably detailed picture of what that early universe must have looked like. According to the standard cosmological model, the universe began in an intensely hot and dense state roughly 13.8 billion years ago. In the first moments after this beginning, matter existed as an energetic soup of particles and radiation. As the universe expanded and cooled, atoms slowly formed, allowing light to travel freely for the first time. This ancient glow still surrounds the cosmos today as the cosmic microwave background, a faint afterglow that carries with it a snapshot of the universe when it was only a few 100,000 years old. After this initial period came what astronomers often call the cosmic dark ages. During this era, the universe was filled mostly with hydrogen and helium gas. Stars had not yet ignited, and galaxies had not yet formed. Gravity, however, was already at work. Slowly and quietly it pulled matter together, gathering gas into denser and denser regions. Over time, these regions collapsed under their own weight, forming the first stars and eventually the first galaxies. The story seemed well understood. Early galaxies were expected to be small, irregular, and primitive. They would have contained relatively few stars, still in the process of assembling themselves from scattered clouds of gas. Larger and more complex galaxies, like the majestic spirals seen across the modern universe, would require billions of years to grow. For many years, this timeline appeared consistent with everything astronomers observed. The earliest galaxies detected by previous space telescopes were faint and small, just as theory predicted. Their light revealed young stellar populations and chaotic structures, the hallmarks of cosmic infancy. Each new observation seemed to confirm the same story. The universe had started simple, and complexity had emerged slowly. Then came a telescope designed to see farther than any instrument before it. The James Webb Space Telescope was built with a single extraordinary purpose. It would look deeper into the universe than any previous observatory, capturing light that had traveled for more than 13 billion years. To achieve this, engineers constructed a mirror over 6 meters wide, composed of 18 gold-coated segments carefully aligned to act as a single reflective surface. This mirror would gather faint infrared light, wavelengths stretched by cosmic expansion as they traveled across immense distances. Positioned far beyond Earth in a delicate gravitational balance point known as Lagrange 2, Webb would sit in permanent darkness behind a vast sunshield the size of a tennis court. Shielded from the warmth of the sun and Earth, the telescope would cool to temperatures cold enough to detect the faintest whispers of ancient starlight. The ambition behind Webb was not merely to see distant galaxies. It was to witness the universe during its earliest chapters, to capture the moment when the first cosmic structures began to emerge from darkness. When the first images from the telescope arrived, they were immediately breathtaking. Deep fields revealed thousands of galaxies packed into tiny patches of sky, some of them so distant that their light had begun its journey when the universe was only a few 100 million years old. At first, Everything seemed to be unfolding exactly as astronomers had hoped. Webb was indeed seeing galaxies that existed astonishingly early in cosmic history. But as researchers began to examine the details more carefully, a subtle unease began to emerge. Some of these galaxies appeared far more massive than expected. Under existing models of galaxy formation, there simply had not been enough time for such large structures to assemble. The early universe was supposed to be a place of small beginnings. Yet the telescope was revealing galaxies that looked strangely mature, systems already containing enormous numbers of stars. In several cases, the estimated masses of these early galaxies rivaled that of the Milky Way, despite existing when the universe was only a fraction of its current age. According to traditional timelines, galaxies should still have been in the earliest stages of growth during this era. Astronomers began to check and recheck the data. Distance measurements were scrutinized. Instrument calibrations were examined. Computer models were revisited. At first, many researchers suspected that the apparent discrepancy must come from some subtle observational effect. But the pattern refused to disappear. Across multiple observations, Webb continued to reveal galaxies that appeared unusually large for their age. Some seemed to have formed stars at extraordinary rates, converting vast quantities of gas into stellar populations within a relatively short cosmic window. The implication was unsettling. If these measurements were correct, then the early universe may have been forming galaxies far more rapidly than existing theories allowed. To understand why this was surprising, it helps to consider how galaxies are thought to grow. In the standard picture, galaxy formation is closely tied to the invisible scaffolding of dark matter. Although dark matter cannot be seen directly, its gravitational influence shapes the large-scale structure of the cosmos. Massive halos of dark matter form first, pulling ordinary matter into dense regions where stars can ignite. Over time, these halos merge together, gradually building larger galaxies through a process known as hierarchical assembly. Small galaxies combine to form bigger ones, and over billions of years, the familiar spiral and elliptical shapes begin to emerge. But this process takes time. Dark matter halos must first grow large enough to capture significant amounts of gas. That gas must then cool and collapse to form stars. Stellar winds and supernova explosions inject energy back into the surrounding environment, regulating how quickly additional stars can form. The entire process is complex and self-regulating, unfolding over immense spans of time. If Webb is truly observing massive galaxies only a few 100 million years after the beginning of the universe, then something about this timeline may be incomplete. One possibility is that early star formation occurred with remarkable efficiency. In the dense conditions of the young universe, clouds of gas may have collapsed more quickly than expected, igniting stars at extraordinary rates. Under such circumstances, galaxies could accumulate mass far faster than current models predict. Another possibility is that the earliest galaxies were dominated by extremely massive stars, far larger than those commonly seen today. These stars would burn brightly but live short lives, rapidly enriching their environments with heavier elements and accelerating the growth of subsequent stellar generations. Some researchers have even wondered whether hidden black holes could play a role in shaping these observations. Supermassive black holes are known to exist at the centers of many galaxies, including the Milky Way. If black holes began growing earlier than expected, their gravitational influence might help funnel gas into intense bursts of star formation. Yet none of these explanations fully resolves the puzzle. Each possibility helps in certain ways, but raises new questions in others. The deeper astronomers examine the data, the clearer it becomes that the early universe may have been far more dynamic than previously imagined. And Webb is only beginning its observations. With every new survey, the telescope continues to reveal galaxies that push against the boundaries of existing theory. Some appear bright and well-structured at times when the universe was still emerging from darkness. Others show signs of complex chemical enrichment, suggesting that multiple generations of stars had already lived and died. These discoveries do not necessarily mean that the foundations of cosmology are wrong. The overall framework describing the evolution of the universe remains remarkably successful. Observations of the cosmic microwave background, the distribution of galaxies, and the expansion of space all align closely with theoretical predictions. But the details of how structure formed within that expanding universe may be more intricate than previously understood. Science often advances in precisely this way. A new instrument extends humanity's vision just a little farther, and in doing so reveals phenomena that earlier theories had never anticipated. Theories then adapt, absorbing the new information and gradually refining the picture of reality. The James Webb Space Telescope is offering exactly this kind of moment. By looking deeper into the cosmos than any telescope before it, Webb is not simply confirming existing ideas. It is exposing the complexity of a universe that may have grown up faster and in stranger ways than anyone had imagined. And somewhere in the faint glow of those ancient galaxies lies a deeper story about how everything began. The discovery forced astronomers into a position that science occasionally finds itself in, a moment where observation begins to move faster than explanation. For years, the early universe had been described using models that appeared to fit almost perfectly with the available evidence. Galaxies formed slowly, growing through mergers and gradual accumulation of matter. The timeline was orderly, predictable, and supported by countless simulations. But when a new instrument extends human sight far enough, that comfortable picture can suddenly begin to fracture. What Webb revealed was not a completely different universe, but one that seemed to mature far more quickly than expected. The galaxies appearing in the telescope's earliest deep field images were not the faint, scattered building blocks researchers had anticipated. Instead, many looked bright and surprisingly structured, systems that already contained enormous numbers of stars. In several cases, the estimated stellar masses were so large that astronomers began comparing them to the Milky Way itself. That comparison was deeply unsettling. The Milky Way is the product of billions of years of cosmic evolution. Its spiral arms, its enormous population of stars, and its vast halo of dark matter all emerged through an extended process of mergers, star formation, and gravitational shaping. To find galaxies approaching that level of mass when the universe was still in its infancy suggested that something in the timeline was either incomplete or misunderstood. At first, the most cautious explanation focused on measurement. Estimating the mass of distant galaxies is not straightforward. Astronomers must analyze the light coming from those galaxies, studying how different wavelengths combine to reveal the age and number of stars present. Small uncertainties in distance or brightness can translate into significant differences in mass estimates. Perhaps these galaxies only appeared enormous because of subtle effects in the data. But repeated observations began to reinforce the same conclusion. Independent teams analyzing different Webb surveys continued to report galaxies that appeared unusually large for their time period. Some were detected less than 500 million years after the beginning of the universe, an era when theory predicted that only modest galactic structures should exist. Yet these objects already seemed to contain vast stellar populations. If the measurements were accurate, then galaxies had begun assembling themselves far more rapidly than expected. This raised an obvious question. What mechanism could allow such rapid growth? One idea centered on the density of the early universe. In its youth, the cosmos was much smaller than it is today. Matter was packed more tightly together, and gravitational interactions occurred more frequently. Under these conditions, gas clouds might collapse more efficiently, triggering intense waves of star formation that could quickly transform a young galaxy into a massive stellar system. Another possibility involved the behavior of the first generation of stars. These earliest stars, sometimes referred to as population 3 stars, are thought to have formed from pristine hydrogen and helium left over from the Big Bang. Without heavier elements to cool the gas clouds from which they formed, these stars may have grown to extraordinary sizes, hundreds of times the mass of the Sun. Such giants would burn fiercely, releasing enormous amounts of energy while rapidly producing heavier elements in their cores. When these massive stars ended their lives in violent supernova explosions, they would scatter those elements back into surrounding space. That enrichment process could dramatically accelerate the formation of later generations of stars, allowing galaxies to evolve more quickly than models based solely on modern star formation might suggest. Yet even this explanation may not be sufficient. The sheer number of stars required to explain some of Webb's early galaxies remains difficult to reconcile with conventional timelines. Forming so many stars so quickly requires not only abundant gas, but also conditions that allow that gas to collapse efficiently without being disrupted by stellar winds and radiation from newly formed stars. Some researchers have therefore begun examining the role of dark matter more closely. Dark matter is believed to make up the majority of matter in the universe, shaping the gravitational landscape in which galaxies grow. If dark matter halos formed earlier or more efficiently than predicted, they might have created deeper gravitational wells capable of drawing gas inward at higher rates. This would provide the raw material necessary for accelerated galaxy growth. Even small changes in the behavior of dark matter during the earliest stages of cosmic evolution could have profound consequences for how quickly structure formed. Another intriguing possibility involves black holes. Today, nearly every large galaxy appears to host a supermassive black hole at its center. These objects can contain millions or even billions of times the mass of the Sun. Their origins, however, remain one of the most puzzling questions in astrophysics. If massive black holes began forming very early in cosmic history, their gravitational pull could channel surrounding gas into dense regions, triggering intense bursts of star formation. In such a scenario, the earliest galaxies might grow rapidly under the influence of both dark matter halos and central black holes, creating massive stellar systems far earlier than previously believed. Still, none of these explanations completely resolves the tension. Each proposal offers part of the story, but the overall picture remains uncertain. Webb's observations may ultimately require adjustments to multiple aspects of galaxy formation theory rather than a single dramatic revision. What makes the situation particularly fascinating is that Webb's discoveries do not overturn the broader framework of cosmology. The expansion of the universe, the cosmic microwave background, and the distribution of galaxies across vast scales all continue to support the existing model of cosmic evolution. Instead, the new observations appear to highlight gaps in the fine details of how the earliest structures assembled themselves. And those details matter. Understanding how galaxies formed in the first billion years of cosmic history is essential for explaining the later evolution of the universe. The earliest galaxies produced the first heavy elements, forged in the cores of stars and dispersed through supernova explosions. Those elements eventually became the building blocks of planets, atmospheres, and life itself. In a very real sense, the rapid growth of early galaxies shaped the conditions that would one day allow worlds like Earth to exist. For now, Webb continues to look deeper. Each new observation adds another piece to the puzzle, revealing galaxies that appear brighter, more structured, and more complex than expected at such early times. The telescope's sensitive instruments are capable of detecting light that has traveled across nearly the entire history of the universe, allowing astronomers to reconstruct the sequence of events that followed the cosmic beginning. Some of those events may prove to be far more dramatic than previously imagined. And as the telescope continues its quiet watch beyond Earth's orbit, it may gradually reveal that the early universe was not a slow and cautious place at all, but a remarkably active environment where galaxies emerged from darkness with surprising speed. As the first wave of analysis settled, astronomers began focusing on a second question that was just as important as the galaxies themselves. If these objects truly existed so early in cosmic history, what exactly did they look like in detail? Their mass was surprising, but their structure could reveal something even more important about how they formed. Webb's instruments are capable of far more than simply detecting distant light. They can break that light into its component wavelengths, allowing scientists to analyze the chemical fingerprints embedded within it. Each element absorbs and emits light at specific wavelengths, leaving patterns that reveal what materials are present within distant stars and gas clouds. By studying these spectral fingerprints, astronomers can determine not only how many stars a galaxy contains, but also how chemically evolved those stars are. This is where the puzzle deepened further. Several early galaxies appeared to contain elements heavier than hydrogen and helium. That fact alone implied that at least one generation of stars had already lived and died inside them. Heavy elements are forged in stellar cores and distributed through explosive events such as supernovae. If those elements were already present, then the galaxies must have experienced multiple cycles of star formation in a relatively short period of time. The implication was remarkable. The universe may have begun producing complex stellar systems almost immediately after the first stars ignited. Astronomers had long believed that the earliest galaxies would appear extremely primitive, composed mostly of pristine gas and very young stars. Instead, some of the systems Webb observed appeared chemically enriched and structurally developed far earlier than expected. That raised a new possibility. Perhaps the first galaxies did not grow slowly at all. Perhaps they formed through bursts of extreme activity, periods in which enormous amounts of gas collapsed inward and ignited stars across entire regions of space simultaneously. Under such conditions, a galaxy could evolve dramatically in a very short span of cosmic time. Computer simulations have begun exploring this scenario. In certain models, dense streams of gas flowing along the filaments of the cosmic web can funnel matter into young galaxies at extraordinary rates. These inflows act like rivers feeding a growing city, continuously delivering fresh material that fuels star formation. If such inflows were stronger or more efficient in the early universe than current models assume, then galaxies could accumulate mass much more rapidly than previously believed. But even this explanation introduces new complexities. Rapid star formation produces enormous amounts of radiation and stellar winds. These forces tend to push gas outward, disrupting the very clouds from which new stars form. In many galaxies today, this feedback process slows the growth of stellar populations. Star formation proceeds in waves rather than unchecked explosions. For early galaxies to build themselves so quickly, that feedback may have behaved differently. Some researchers have suggested that the dense conditions of the young universe allowed gas to remain bound within galaxies despite intense stellar activity. Instead of being blown away, the gas may have been trapped by strong gravitational fields, allowing star formation to continue almost uninterrupted. Others have proposed that early galaxies may have been far more compact than modern ones. In smaller volumes, gravity would act more strongly, helping to retain gas and sustain high star formation rates. Then there is the question of the telescope's measurements themselves. Astronomers determine distances to extremely remote galaxies by measuring how much their light has been stretched by the expansion of the universe. This stretching, known as redshift, shifts light toward longer wavelengths. The greater the redshift, the farther away and earlier in time the galaxy must be. However, interpreting redshift can sometimes be challenging, particularly when dealing with faint objects whose light is only barely detectable. Some scientists initially wondered whether certain early galaxies might actually be closer than they appeared, their light affected by unusual conditions that mimicked extreme distances. Yet as more observations accumulated, that explanation became harder to maintain. Webb's spectroscopic instruments began confirming the distances of several candidate galaxies with remarkable precision. The signals matched what astronomers would expect from objects that truly existed within the first few 100 million years of cosmic history. The galaxies were not illusions. They were real structures shining across the deepest reaches of time. That realization forced astronomers to confront a broader philosophical truth about scientific progress. Models of the universe are not final answers. They are frameworks that evolve as new evidence appears. When observations challenge those frameworks, the goal is not to defend the models at all costs, but to refine them until they better describe reality. The James Webb Space Telescope is providing precisely the kind of evidence that drives that process. Every deep field image contains thousands of galaxies, each representing a different moment in cosmic history. Some appear exactly as theory predicted, small and faint systems still assembling their first stars. Others, however, seem unexpectedly large or chemically evolved, suggesting that the early universe may have hosted a much richer diversity of galaxies than previously imagined. This diversity may ultimately prove to be the key. Rather than assuming that all galaxies formed in the same gradual way, astronomers are beginning to consider that multiple pathways to galaxy formation may have existed. Some systems may indeed have grown slowly through mergers and steady star formation. Others may have experienced dramatic bursts of activity, assembling enormous stellar populations in surprisingly short times. The universe, after all, rarely follows a single, simple pattern. Across billions of light-years, conditions vary from region to region. Slight differences in density, temperature, and dark matter distribution can lead to dramatically different outcomes. In some regions, galaxies may grow quietly over billions of years. In others, they may ignite rapidly, creating massive structures long before the cosmic average would suggest. Webb's observations may therefore be revealing the most extreme examples of early galaxy formation rather than the typical case. Even so, these extreme examples are valuable. By studying them, astronomers gain insight into the physical processes that govern the birth of galaxies. Understanding how gas flows through dark matter halos, how stars ignite within dense clouds, and how radiation shapes the surrounding environment are all essential pieces of the larger cosmic story. And the deeper Webb looks, the more pieces of that story begin to appear. Beyond the earliest galaxies already identified, astronomers are now pushing toward even more distant candidates. Some observations hint at galaxies that may have existed less than 300 million years after the beginning of the universe. If confirmed, such discoveries would push the boundaries of galaxy formation to even earlier times. Each potential detection triggers careful analysis. Researchers compare observations against simulations, testing whether current models can reproduce what Webb is seeing. Sometimes the models succeed. Sometimes they reveal subtle mismatches that hint at new physics waiting to be understood. This iterative process lies at the heart of scientific discovery. The telescope provides the data. Theories attempt to explain that data. When mismatches appear, new ideas are developed, simulations are adjusted, and further observations are conducted. Gradually, the picture sharpens. In the coming years, Webb will conduct deeper surveys, mapping enormous regions of the sky with unprecedented sensitivity. These surveys will reveal not only individual galaxies, but also how those galaxies are distributed across the cosmic web, the vast network of filaments and voids shaped by dark matter. By tracing that structure backward through time, astronomers hope to understand how the first galaxies emerged from the primordial universe. And somewhere within that emerging picture lies the answer to a deceptively simple question. How did the universe grow from a nearly uniform cloud of hydrogen into a cosmos filled with galaxies, stars, planets, and the complex structures seen today? The James Webb Space Telescope is now helping to reveal the earliest chapters of that transformation. As more Webb observations were released, another layer of the puzzle slowly began to emerge. It was not just the mass of early galaxies that surprised astronomers, but also the sheer brightness of some of them. When a galaxy appears bright at enormous distances, it usually means that large numbers of stars are forming within it. Young stars shine intensely, especially the most massive ones, pouring energy into the surrounding gas and illuminating entire regions of space. In the nearby universe, bursts of rapid star formation are well known. Astronomers call these starburst galaxies. In such systems, stars form at rates hundreds of times faster than in calmer galaxies like the Milky Way. These bursts are usually triggered by gravitational interactions or collisions between galaxies, events that compress gas clouds and ignite waves of stellar birth. But in the earliest universe, galaxies were not yet numerous enough to be colliding frequently. The cosmic landscape was still young, its structures only beginning to assemble. Finding galaxies that appeared to be undergoing intense star formation during this early era therefore introduced another complication. Something had to be driving these rapid bursts of stellar creation. One possibility involves the large-scale structure of the universe itself. Matter is not distributed randomly across space. Instead, it forms a vast network known as the cosmic web. This web consists of enormous filaments of dark matter and gas that stretch across millions of light years. Galaxies tend to form at the intersections of these filaments, where matter flows inward from multiple directions. In the early universe, these flows may have been especially powerful. Gas streaming along the filaments could feed young galaxies continuously, supplying the raw material needed to form stars at remarkable speeds. Instead of relying on occasional collisions with neighboring galaxies, early systems may have been nourished by steady rivers of matter drawn in by gravity. Such inflows would allow galaxies to grow far more quickly than expected under traditional models that assume slower accumulation of gas. Another factor may lie in the way early stars influenced their surroundings. When massive stars ignite, they release enormous amounts of radiation. That radiation heaps nearby gas, often preventing it from collapsing into new stars. This feedback process acts as a natural regulator of star formation, limiting how quickly galaxies can build their stellar populations. However, in the extremely dense environment of the early universe, this feedback may have behaved differently. Gas clouds may have been so abundant that radiation from young stars could not easily disperse them. Instead of halting star formation, the surrounding gas might simply have continued collapsing under gravity, allowing new stars to form continuously. If this process occurred across entire galaxies, it could produce stellar populations much larger than previously anticipated. Meanwhile, astronomers began noticing another intriguing feature within Webb's deep images. Some early galaxies appeared surprisingly compact. Their stars were packed into relatively small regions compared with modern galaxies of similar mass. This compactness could be an important clue. When matter is confined to a smaller space, gravity becomes more intense. Stronger gravitational fields can help retain gas within a galaxy, preventing it from escaping during energetic star formation events. In such an environment, the cycle of gas collapse and star birth might proceed rapidly without being disrupted. Compact galaxies could therefore act as efficient star factories, converting enormous quantities of gas into stars within relatively short periods. These ideas remain the subject of active research. Astronomers are currently running increasingly sophisticated simulations to test how galaxies might behave under such conditions. Modern supercomputers allow researchers to recreate large volumes of the universe in virtual form, tracking the behavior of dark matter, gas, and stars over billions of years of simulated time. By comparing these simulations with Webb's observations, scientists can evaluate which physical processes best reproduce the structures now being detected. In many cases, the simulations are beginning to show that extremely rapid galaxy growth is not impossible after all. Under certain conditions, galaxies can indeed accumulate large stellar masses within a few 100 million years. But achieving this requires combinations of factors that earlier models did not fully explore. This does not mean that the fundamental understanding of the universe must be discarded. Rather, it suggests that the early stages of galaxy formation may have been more diverse and more energetic than previously assumed. In fact, there are hints that the early universe may have experienced periods of extraordinary activity, brief epochs during which star formation surged across many regions simultaneously. These cosmic episodes would leave behind galaxies that appear unusually bright and mature even at very early times. Evidence for such activity may already exist. Astronomers studying Webb data have identified regions where multiple young galaxies appear clustered together. These clusters may represent the earliest stages of large-scale structure formation, areas where matter gathered rapidly under the influence of dark matter. Within such environments, the conditions for galaxy growth could have been especially favorable. Dense regions would accumulate gas quickly, providing a continuous supply of material for star formation. Galaxies within these regions might also interact gravitationally with one another, triggering further bursts of activity. Over time, these early clusters could evolve into the massive galaxy groups and clusters observed across the modern universe. Another line of investigation focuses on the role of dust. Dust grains form when heavy elements produced inside stars are expelled into surrounding space. These tiny particles absorb and scatter light, often making galaxies appear dimmer than they actually are. In some cases, dust can obscure large portions of a galaxy's star-forming regions. If early galaxies contained less dust than modern ones, their light might escape more freely, making them appear brighter than expected. Alternatively, if dust is present but distributed differently, it could influence how astronomers interpret the brightness and mass of distant galaxies. Understanding the amount and distribution of dust in early galaxies is therefore crucial for interpreting Webb's observations accurately. The telescope's infrared capabilities are particularly useful in this regard. Infrared light can penetrate dusty regions more easily than visible light, allowing astronomers to see deeper into star-forming clouds. By analyzing the infrared signatures of distant galaxies, researchers can estimate how much dust they contain and how it affects their appearance. These measurements will help determine whether some early galaxies only appear unusually massive because their starlight is being interpreted in unexpected ways. At the same time, Webb is also providing insight into the earliest black holes. Supermassive black holes have been detected in galaxies that existed when the universe was less than 1 billion years old. The presence of such enormous objects so early in cosmic history presents a challenge similar to that posed by massive early galaxies. Growing a black hole to millions or billions of solar masses requires time and a steady supply of material. If black holes already existed at such sizes during the universe's youth, they must have grown extraordinarily quickly. This raises the possibility that black holes and galaxies evolved together from the very beginning. As galaxies accumulated gas and formed stars, some of that gas may have spiraled inward toward central black holes, feeding their growth. In turn, Energy released by matter falling into black holes could influence the surrounding galaxy, regulating star formation and shaping its structure. This relationship between galaxies and black holes remains one of the most fascinating aspects of modern astrophysics. Webb's observations may soon reveal how early this partnership began. By identifying faint signals from active black holes in distant galaxies, astronomers can determine whether these objects were already influencing galaxy evolution within the first few 100 million years after the Big Bang. If so, the growth of galaxies and black holes may have been intertwined from the earliest stages of cosmic history. And as these investigations continue, a broader realization is slowly taking shape. The early universe may not have been a quiet place waiting patiently for complexity to emerge. Instead, it may have been a remarkably active environment where gravity, gas, radiation, and dark matter interacted in ways that produced galaxies with surprising speed. The picture that once seemed so simple is gradually becoming richer. Each new observation from the James Webb Space Telescope reveals a cosmos that is both familiar and unexpected. The overall structure of cosmic history remains intact, yet the details of how the first galaxies assembled themselves are becoming far more intricate than earlier theories imagined. This is precisely how scientific understanding evolves. New instruments expand the boundaries of observation, revealing phenomena that demand deeper explanation. Theories adapt, simulations grow more sophisticated, and gradually a more accurate picture of reality emerges. Webb has only just begun its mission, yet it is already transforming humanity's view of the early universe. Some of its discoveries will confirm what astronomers long suspected. Others will challenge long-held assumptions about how the first galaxies formed and how quickly the cosmos matured. And with every new glimpse into the distant past, the story of the universe continues to unfold. One of the most valuable aspects of Webb's observations is that they allow astronomers to compare galaxies across different stages of cosmic history within a single dataset. Because light from distant galaxies has traveled for billions of years, every image captured by the telescope contains objects from many different eras. Some galaxies appear as they existed a few billion years after the beginning of the universe, while others reveal conditions from much earlier periods. By examining these populations together, astronomers can trace how galaxies evolved over time. The earliest galaxies appear small and irregular in many cases, which still aligns with long-standing expectations. But scattered among them are systems that seem to have advanced much further along the path of development. These galaxies display bright central regions, extended star-forming structures, and in some cases, hints of organized shapes beginning to emerge. This variety suggests that galaxy formation may not have followed a uniform schedule. Some regions of the universe may have experienced conditions that accelerated growth dramatically. Where gas density was slightly higher, or where dark matter halos formed earlier than average, galaxies could have gained a head start. Over millions of years, that early advantage would compound, producing systems that appear unusually mature when compared with their cosmic neighbors. Astronomers often refer to this concept as cosmic variance. Even though the laws of physics operate the same way everywhere, the distribution of matter across the universe is uneven. Some regions are naturally denser, while others contain far less material. These differences can influence how quickly structures grow. In denser regions, galaxies would have more gas available for star formation and more nearby objects with which to interact gravitationally. Both factors encourage rapid growth. Meanwhile, galaxies forming in less dense environments would evolve more slowly. Webb's deep surveys are beginning to map these variations with remarkable clarity. By analyzing how galaxies cluster together at different distances, astronomers can reconstruct the large-scale environment in which they formed. If the earliest massive galaxies tend to appear in particularly dense regions, This could explain why they developed faster than expected without requiring a complete revision of cosmological theory. Another key area of research involves the role of cooling. For gas clouds to collapse and form stars, they must lose heat. Cooling allows the gas to compress under gravity until nuclear fusion ignites within the forming stars. In the modern universe, heavy elements such as carbon and oxygen help facilitate this cooling process. These elements emit radiation efficiently, allowing gas clouds to shed energy and collapse. But in the earliest universe, such elements were scarce. The first stars formed from almost pure hydrogen and helium. Under these conditions, cooling is less efficient, which should slow the rate at which gas clouds collapse. This is one reason astronomers originally believed that early star formation would proceed gradually. However, there may have been additional cooling mechanisms at work. Molecules such as molecular hydrogen can also radiate energy and assist with cooling under certain conditions. If molecular hydrogen formed more efficiently than previously assumed, it could have allowed gas clouds to collapse faster than expected, accelerating the birth of the first stars and galaxies. Recent theoretical studies have begun exploring this possibility. Under particular circumstances, the chemistry of the early universe may have allowed molecular hydrogen to accumulate within dense regions of gas. This would enhance cooling and enable rapid gravitational collapse, potentially producing large stellar populations within relatively short time spans. Such processes would help explain why some galaxies appear surprisingly mature, even during the universe's earliest epochs. At the same time, astronomers are examining whether certain early galaxies might be powered by intense episodes of star formation that temporarily inflate their apparent brightness. If a galaxy forms stars at an extreme rate for a brief period, it can appear far more luminous than usual. This luminosity can make the galaxy seem larger and more massive when first observed. Over time, however, the burst subsides and the galaxy settles into a quieter state. If Webb happens to be capturing galaxies during these short-lived bursts, it might explain why they appear unusually bright and massive compared with expectations. Determining whether this is the case requires careful observation across multiple wavelengths of light. By analyzing how the brightness of a galaxy changes at different wavelengths, astronomers can estimate how rapidly stars are forming and how long those bursts are likely to last. These measurements help distinguish between galaxies that are genuinely massive and those that simply appear bright because of temporary star formation events. Another fascinating line of investigation concerns the geometry of early galaxies. Many galaxies in the modern universe exhibit familiar shapes such as spirals, ellipses, or irregular clusters of stars. These structures arise through long periods of gravitational interaction and rotation. Spiral arms, for example, develop as rotating disks of gas and stars settle into stable patterns over billions of years. In the earliest galaxies, such organized structures were not expected to exist yet. The systems should still have been chaotic collections of stars forming within turbulent gas clouds. Yet Webb has revealed hints that some galaxies may already possess rotating disks even in the early universe. If confirmed, this would imply that ordered motion emerged far earlier than previously thought. Rotating disks allow gas to flow inward toward the center of a galaxy while maintaining overall stability. This process can sustain star formation over long periods and may contribute to the rapid accumulation of stellar mass. Understanding when and how these disks formed will provide important insight into the mechanics of early galaxy growth. Astronomers are also studying the distribution of elements within early galaxies to determine how quickly stellar generations enriched their environments. Each generation of stars produces heavier elements and disperses them into surrounding gas. Over time, this enrichment process gradually increases the complexity of galactic chemistry. By measuring the abundance of elements such as oxygen and carbon in distant galaxies, researchers can estimate how many cycles of star formation have already occurred. If significant enrichment is detected at extremely early times, it would indicate that multiple generations of massive stars lived and died in rapid succession. Such rapid cycles would further support the idea that the early universe experienced bursts of extraordinary stellar activity. All of these investigations point toward the same emerging conclusion. The first billion years of cosmic history may have been far more dynamic than once believed. Rather than slowly assembling simple structures that gradually evolved into galaxies, the universe may have produced a wide spectrum of galactic environments from the very beginning. Some galaxies likely grew slowly, following the steady path predicted by traditional models. Others may have experienced intense periods of growth driven by dense environments, efficient cooling, or powerful inflows of gas. The result would be a cosmos filled with diversity even at its earliest stages. This diversity is exactly what Webb is beginning to reveal. With each observation, astronomers gain a clearer picture of how the first galaxies behaved. Some discoveries confirm expectations. Others highlight surprising possibilities that challenge previous assumptions about the pace of cosmic evolution. And as the telescope continues its survey of the distant universe, the boundary between what was once considered early and what was once considered mature may gradually shift. Galaxies that once seemed impossibly advanced for their age may simply represent the fastest-growing members of a population whose full complexity is only now coming into view. The early universe, it seems, may have been capable of far more rapid transformation than anyone previously imagined. What makes these discoveries particularly powerful is not simply that they challenge expectations, but that they provide a direct window into the most formative period of cosmic history. The first billion years after the beginning of the universe determined how matter would organize itself for the rest of time. During that era, the earliest stars ignited, the first heavy elements were forged, and the first galaxies began to shape the large-scale structure of the cosmos. Understanding that period is therefore essential for understanding everything that followed. The galaxies now being observed by the James Webb Space Telescope are not merely distant objects. They are the ancestors of the vast galactic population seen throughout the modern universe. Every spiral galaxy, every elliptical system, and every cluster of stars ultimately traces its origins back to processes that began during those early epochs. By studying these distant systems, astronomers are effectively examining the first drafts of cosmic architecture. One of the most striking lessons emerging from Webb's observations is that the universe appears capable of producing complexity very quickly. Within only a few 100 million years after the beginning of cosmic expansion, gravity had already gathered matter into structures capable of forming enormous numbers of stars. In some regions, those stars may have been born in rapid waves, transforming simple clouds of gas into luminous galaxies at remarkable speed. This rapid transformation carries profound implications. If galaxies formed quickly, then the enrichment of the universe with heavy elements may also have progressed more rapidly than once assumed. The earliest generations of stars would have produced carbon, oxygen, silicon, and other elements that later became the building blocks of planets and atmospheres. Every atom of oxygen in Earth's oceans, every grain of iron within its core, was forged in stars that lived long before the solar system existed. Those processes began inside the first galaxies. By tracing how early galaxies formed and evolved, astronomers are also tracing the origin of the chemical ingredients that eventually allowed complex worlds to arise. Another important consequence involves the growth of cosmic structure itself. Galaxies do not exist in isolation. They are linked together by the immense network of dark matter filaments that span the universe. As galaxies grow, they influence the distribution of gas and matter around them, shaping the environment in which future generations of galaxies will develop. Early galaxies therefore act as seeds from which larger structures emerge. Clusters of galaxies, enormous systems containing hundreds or thousands of members, began as small concentrations of matter during the universe's youth. If some galaxies formed earlier and grew more quickly than expected, those early systems may have played a crucial role in shaping the large-scale cosmic landscape that followed. The Webb telescope is now allowing astronomers to witness the earliest stages of that process. In the coming years, the telescope will conduct increasingly deep surveys, examining vast regions of the sky with unprecedented sensitivity. These surveys will reveal not only individual galaxies, but entire populations, spanning different stages of cosmic development. By comparing these populations, researchers will be able to reconstruct how galaxies evolved from their earliest beginnings into the structures seen across the modern universe. Alongside Webb, other observatories will contribute additional pieces of the puzzle. Future telescopes on Earth and in space will measure the motion of gas within distant galaxies, analyze the growth of early black holes, and map the distribution of dark matter with greater precision. Together, these observations will help determine which physical processes drove the rapid formation of the first cosmic structures. Over time, a clearer picture will emerge. Perhaps the early universe truly did produce galaxies more efficiently than earlier models suggested. Perhaps dense regions of the cosmic web channeled gas inward at extraordinary rates, fueling bursts of star formation that built massive galaxies in record time. Or perhaps subtle aspects of dark matter, cooling physics, or stellar evolution played larger roles than previously understood. Whatever the final explanation, the process of discovery is already reshaping humanity's understanding of the universe. For much of the 20th century, astronomers believed that the early cosmos was relatively simple, a quiet stage in which small galaxies slowly assembled before evolving into the vast structures seen today. The deeper humanity looked, however, the more that simplicity began to dissolve. The James Webb Space Telescope has extended that view farther than ever before. By capturing light that began its journey more than 13 billion years ago, Webb is revealing a universe that was already busy transforming itself even in its earliest chapters. Galaxies were forming, stars were igniting, and heavy elements were spreading through space, laying the groundwork for everything that would come later. The telescope's discoveries do not signal the end of cosmological understanding. Instead, they mark the beginning of a new phase in which astronomers refine their models using the most detailed observations ever obtained. The universe is still telling its story. Every distant galaxy captured in Webb's images represents a moment from a time when the cosmos was still young, when the first structures were emerging from darkness. Each one offers a clue about how gravity, gas, and radiation combine to shape the cosmic landscape. As these clues accumulate, the early universe becomes less of a distant mystery and more of a visible chapter in the unfolding history of reality. And perhaps the most remarkable aspect of all is that this history is still being written in the faint light arriving from the edge of the observable universe. Light that traveled across billions of years before finally reaching the mirrors of a telescope quietly watching from deep space.